Uh, Hello, everyone. Good morning. Everyone's having a good Ignite? Yeah. Perfect. Okay. Hey, look. My name's Karan. I'm a principal product manager in the Surface team, and this is.
I'm David Abzarian, the chief architect for Microsoft Surface.
And we've done this a few times, so we like to joke that together, actually, we have about almost 50 years at Microsoft. But super excited to be here, talking to you about our security story in Surface, but also how it plays into sort of the Windows story. And just to kind of orient you, right, in terms of what we're going to do today, we're going to be telling a story in three parts. The first part is we'll be talking to you about how we think about security in the Surface team, what are our principles, and how they play into sort of the overall, the big umbrella of Microsoft. Second, we'll deep dive into the security story for our in-market devices. So this is stuff that you can go out and buy today. What makes them unique, and we believe best in the industry. And then finally, and most excitedly for the two of us at least, we'll be giving you a peek into what we're going to be doing in the future. So you'll get sort of an insight into what's coming next year and then on and on. To begin, I wanted to actually start with this quote from Satya. Satya emphasizes in this quote that we have a unique opportunity and responsibility to build the most secure and trusted platform. This isn't optional, it's core to our business and mission. For Surface, this means every design choice, every feature, every update is about reinforcing that trust. From secure sign-in experiences like Windows Hello that we ship on all of our devices, to turning on security capabilities in Windows, to writing our own firmware, we are delivering confidence at every touch point. We build Surface to be the most secure and trusted platform for our customers. Every decision we make helps earn and maintain that trust. Security is the top priority for Microsoft through the Secure Future initiative, and Surface brings the security vision to life in every device, from chip to cloud. Every Surface device is built on three foundational principles. Secure by design, security starts at the architecture level. We design hardware, firmware, and software with security baked in, not bolted on. Secure by default, devices ship with security features enabled out of the box, reducing risk without requiring extra steps from IT or end users. And finally, secure operations. We continuously monitor, update, and respond to threats, ensuring compliance and resilience without adding complexity. Because Microsoft designs and maintains the full stack, firmware, OS, and the cloud, Surface devices help reduce vulnerabilities, accelerate response, and simplify compliance without adding complexity. Now, the Secure Future Initiative report, this was published about a week ago, is our annual deep dive into Microsoft security strategy, culture, and progress. It offers a transparent snapshot of Microsoft security strategy, culture, and progress, showing the innovations help customers and partners strengthen their defenses. This year, it includes insights on Windows and Surface innovations from the hardware level protections to cloud integrated security. You'll see how these advancements reduce risk and simplify compliance. I encourage you to read the report, and actually also a partner blog along with that, authored by my friend over here, David, and our colleague in Windows, Catherine Holsworth. Next, I'm going to hand over to David for a deep dive into how we think about building secure devices at Surface.
Thanks, Karan. I'm going to start off today by framing how Surface approaches security, by talking a little bit about our development principles, and mainly how we focus our investments. Our team scrutinizes the design decisions we make through a set of review boards, once for fundamental architecture and then again for security. This is how we fulfill our commitment to be secure by design and by default. We employ a principle of zero trust. We always validate integrity, always validate identity, and use a mindset of least permissions. You'll hear us reference open source quite a bit today, and that's connected to our principle of transparency. The more eyes on core functionality, the more secure it can be. We extensively partner with Windows to help bring security innovations to scale, and then continually learn from our in-market customers to make those best in class. Kaizen, or continuous improvement, is essential. Surface devices not only get more secure generation over generation, but their security posture improves in market through the servicing that we do. That ethos is all intrinsic in the three pillars where we are investing to be first and best, delivering security value for all of our customers. Secure posture, this means ensuring Surface devices are configured to exercise the best security posture with Windows. This starts with electing the most secure options for all OEM configurability, but extends to everything Surface ships in the OS, including leveraging Windows Update to ensure all our drivers and firmware are always up to date and always secure. Security delighters, we think of these as innovations that not only add security value, but also improve usability and efficiency. A few examples of this are Windows Hello face authentication with enhanced sign-in security, and Security Copilot, built right into the Surface Management Portal, making it easier for enterprise admins to assess the health and security of their fleet. Lastly, and arguably most important, is the secure foundation. This picture helps illustrate it well. The hardware and firmware which Windows depends on are the foundation of a secure PC. What I love most about a Surface device is that we craft every one of these layers in-house to be secure by design and by default. This starts before we even write our first line of embedded code, through the selections we make for embedded controllers, how components will be physically connected, and other aspects of the hardware build. At the next layer, we don't license an off-the-shelf BIOS UEFI implementation. It's the opposite, in fact. We author and scrutinize every line of code in-house at Microsoft and then make that available open source for other PC OEMs. This same principle applies to the firmware for our embedded controllers, and I'm going to share more on that later. First, Karan and I are going to walk you through what we have done at these lower layers such that all the Surface devices we ship are secured core PCs. This means they're designed to block sophisticated firmware attacks, launch in a safe state, and protect critical data. Virtualization-based security and memory integrity protects vital OS resources and security assets, in addition to Windows Hello and BitLocker protecting user identities and data respectively. This is all supported by a hardware-backed root of trust, which brings us to the topic of TPMs. Karan is going to talk a little more about some of the improvements we've made for the secure foundation of recent Surface devices and the rationale for where we're headed next.
Thank you, David. I want to start off by talking about our TPM strategy. Now, if you've been following sort of our commercial devices that we've been building in Surface over the years, you've probably noticed that historically we used to select what we call as discrete TPMs for our devices, and that's where, like, if you look in that box, where the TPM box would actually be outside of the SoC. Now, on YouTube, actually, you can find pretty easily people who have hacked BitLocker pretty quickly because you can pick the device apart and actually do what we call a bus sniffing attack against the discrete TPM, and you can pull the data out. Now, if you know how to deal with that, you can manage that risk. But we would like our devices to be secure by default, and that's the reason why we are starting to select what we call as integrated TPMs. Now, an integrated TPM is just like a discrete TPM in many respects. It's just inside the SoC box, and therefore much harder or nearly impossible for someone to actually do that bus sniffing attack. Additionally, we have Pluton security processor on all of our devices, which is serviced end-to-end by Microsoft, which helps us respond quickly to emerging threats. Next, I wanted to talk about moving up the stack. I want to talk about the firmware layer. As David mentioned, at Microsoft, we build our own UEFI. We don't get it from an IBV. We build it ourselves, and then we open source it. That gives us a solid, transparent foundation to work from. Because we build our own firmware, we can focus on security throughout the life cycle of the product. This is why we were not vulnerable to the logo fail attack. Some of you may have heard of that a couple years ago. We just didn't have the logic in UEFI to be exploited because a Microsoft developer made the right decision to not include that code. We are also increasing adoption of Rust in our firmware, which is known for being memory safe, and we'll talk a lot more about that in following slides. And we push updates fast and reliably through Windows Update. And then finally, we provide great manageability story for our firmware with SEM and DFCI that let you manage and secure your firmware settings. Let's dive into those two technologies a little bit more. SEM, or Surface Enterprise Management Mode, is a feature designed specifically for Surface devices to enhance security and manage firmware settings. SEM is designed to integrate with on-premises endpoint management solutions like ConfigMan, and it allows IT to centrally configure and enforce UEFI settings on Surface devices. Think of it as a way to lock down critical firmware config. This includes locking the end user out of the firmware settings or disabling hardware subsystems like cameras and microphones. There are a few ways to deploy SEM configuration packets to end-user devices. Typically, you would start with what we call the UFI configurator, which is now available as part of the Surface IT toolkit. You create a package and configure all the things that you want enabled or disabled, and then you would deploy them to end-user devices through either PowerShell, WinPE, or as a Windows installer package or an MSI package. And finally, SEM also provides the ability to dynamically disable USB-C on supported devices and docks. Now let's look at DFCI, Device Firmware Configuration Interface. This, you can think of it as the cloud equivalent of SEM in many respects. It enables you to do many of the things you can do with SEM, but from cloud-based management solution, Intune. DFCI is designed to be far easier to deploy than SEM, as it does not require you to provision any PKI infrastructure or design automation or scripts to deploy it. All you have to do is ask your partner to enable autopilot on your devices. Everything else just works. Finally, DFCI is designed with cloud management ethos in that it deploys to the end user devices with a zero-touch experience. There are no prompts or no user experience for the end user to have to go through. And all of this is done while maintaining the really high security bar that we set for ourselves when we designed SEM in the almost about 10 years ago now. Next, we'll start looking at our future investments, and David is going to get us started by giving us a primer on memory safety.
Thanks, Karan. One question I have for everybody is, before we jump into one of my favorite topics, I have a question which is, showing of hands, how many people were impacted or had to deal with the logo fail vulnerability? Interesting. So I guess for those of you, everyone who didn't raise their hand, logo fail was actually a set of vulnerabilities in UFI firmware. It was specifically within the image parsers for how you display boot logos. What was really important about this is it allowed arbitrary code execution, and specifically in the Dixie phase. That's well before the OS loads, and that's the perfect opening for a rootkit and a whole world of trouble. Now, as I said earlier, at Microsoft, we author our own UFI firmware based on the open source project Mu. That doesn't just give OEMs a solid and transparent foundation to work from, it puts them in complete control of what functionality they will enable. So when the logo fail vulnerability was making the rounds and just about every Windows and Linux device was vulnerable, Surface devices weren't among them, and that's because we didn't elect to include the code. Now, logo fail, like many other vulnerabilities, exists because of memory safety issues. We don't always have the luxury of not including a specific parser or piece of functionality, so protection against this class of issues is essential. For the best explanation of memory safety in less than 30 seconds, I'm going to defer to David Weston. He's our CVP of Enterprise and OS Security at Microsoft, and this is from a recent video he published called Windows 2030.
Last, that is really, to me, one of the most important is a concept we call memory safety. Today, roughly 70 to 75% of the vulnerabilities that you have to patch are buffer overruns or computational errors leading to corruption of computer memory. The way memory safety will protect customers is really twofold, or benefit customers. One is 70, 75% of attacks will just no longer apply. The second thing that I think is really beneficial is a lot of our time today as IT professionals is spent patching things. If we have 70 to 75% less things to patch, imagine what we could do.
Now, just to provide some more details and some more context into this, this is a study from Microsoft Research, or MSRC, sorry, about 6 years ago that shows that the statement that David was making, 70% of vulnerabilities or more are simple memory safety issues, right? And it's not just Microsoft. Other industry partners have also acknowledged the importance of memory safety, and government agencies as well. Now, at this point, you might be asking, still, at this point, this all seems rather hypothetical. Is this problem even a real problem? And emphatically, the answer is yes, right? So this is just a sample, not the complete list of memory safety issues that have been reported in the EDK2 code base. EDK2 is sort of the open source UFI that most people today derive from, right? So almost every UFI that is out there deployed has been vulnerable to these things, and these are all memory safety issues. And again, these are not, this is not like a comprehensive list by any means. This is just like a quick sample. And now I'm going to hand it back to David, and he'll tell us what we're going to do about this.
Thanks, Karan. When we talk TPM, Pluton, or about the future of firmware and drivers, you're going to hear Rust a lot. Rust is a memory-safe programming language represented by our mascot friend Ferris in the corner. He's a crustacean, Rustacean. It allows developers to find and address problems at compile time rather than after the code ships. So no doubt there is a learning curve for development teams to get up to speed with Rust, but the return on investment is very high. Rust shines in low-level scenarios because it's really performant. It leads to improved reliability and allows developers granular control of memory, such as whether data is on the stack or at the heap at compile time. If there's one concept I'd like you to take away about Rust, it's the memory ownership and borrowing system, which is at the heart of memory safety without a garbage collector, and it's what makes Rust so good at concurrency. In this simple example, the ownership of V is moved to V2. After the move, Rust considers V as no longer valid, and therefore attempting to use V will cause that E382 error, because V no longer owns the array. This is all enforced at compile time by Rust's borrow checker. At any given time, a resource can either have one mutable reference, meaning it's exclusive write access, or it can have a number of immutable references, meaning shared for read access. The borrow checker is also ensuring that references are valid and point to data that is still in scope. So this is what prevents dangling pointers and use after free errors. The takeaway here is that WDR raises the security baseline for every driver that is built with it, eliminating entire classes of memory-related vulnerabilities before they ship. This means fewer crashes, fewer security incidents, and a more reliable experience for everyone. And in that spirit, Surface is leveraging Rust in numerous ways. In terms of secure foundation, we have a lot happening. Surface is proud to be a contributing member of ODP, the Open Device Partnership. That's a forum where hardware, firmware, and software all meet to build memory-safe implementations of critical PC components. This starts with the embedded controller, also known as MCU or microcontroller unit. This manages so much behind the scenes when you press the power button, before the OS is booted, and throughout the device lifecycle. We've written this from the ground up in Rust and made it open source. You may see this referenced on GitHub as Secure Embedded Controller. At the heart of handling power management, battery, fans, keyboard input, GPIOs, and a variety of other functions is Embassy OS. This is an open source framework for embedded applications that uses Rust and its async facilities, allowing for easy and efficient multitasking. Tasks get transformed at compile time into state machines that run cooperatively. It obsoletes the need for a traditional runtime OS with kernel context switching, and it results in faster and smaller code. There's actually some really, really good studies out there showing dramatic improvements across the board in terms of interrupt latency, thread time, and static memory requirements. This is a 10,000-foot view of how the secure embedded controller is architected with Embassy. The Embassy project maintains HALs, hardware abstraction layers, for many embedded controllers. However, you can still use HALs from other projects with Embassy. We then introduce two concepts in the layer map: services and subsystems. The services house common platform and hardware-independent functions that may be leveraged by various subsystems. Examples are things like HID, component firmware update, debug, temperature, battery, fans, telemetry, and host communication, just to name a few. We also have embedded services which provide the building blocks for creating new services, such as the subscriber-publisher mechanisms and the inter-process communication and the fabric there that allows the services to talk to one another. The subsystems then represent entire functional areas built on a grouping of these services. So for instance, a thermal subsystem may be a combination of temperature, battery, fans, and host comms. With that really quick understanding of the various constructs of the secure EC architecture, we're going to look at one example end-to-end. And in this case, it's the keyboard subsystem. This subsystem has the elements you would expect: a function to do the key scanning from the matrix and a function for managing reporting key states. This leverages some of the key services: HID, to be able to handle the output reports and feature reports, which may indicate things like turn on the caps lock LED. And it also handles the generation of input reports for the make and break of information based on key state. For completeness, this also leverages the HID manager, subsystem, which takes care of our descriptors and packaging of the various HID reports from the services. That subsystem, in turn, leverages the host comm service for transmit receive, which in turn leverages the appropriate subsystem, in this case I2C, to put and pull things off the wire. The key takeaway here is that this enables significant reuse through common functionality. For instance, if I showed you a touchpad subsystem, you'd see a lot of overlap. And that's by design and completely intentional. But it also allows an incredible level of flexibility. So through the abstractions, if a new bus came along, let's say tomorrow like I3C, we'd simply add an I3C subsystem, making it transparent for all the other subsystems and services. Continuing the journey on improvements to our secure foundation, I'm going to hand it back to Karan to talk about another exciting project called codename Patina.
Thank you, David. Really excited about Patina, but before we talk about what is Patina, I wanted to sort of put it in sort of historical context, right? In that chart, sort of tongue-in-cheek, but it's real as well in the sense that before the 2000s, like if you were buying a PC, it came with what we used to call BIOS back then. It was all sort of hand-coded assembler. No one shared that source code with anyone. It was proprietary and custom for like every single PC out there, right? From sort of the mid-2000s on, we have been in the UFI era, and in UFI, most of the UFI is written in C. There's a good amount of open source UFI out there, and there's a lot more code sharing as well. And then finally, now with, especially with Patina, we feel like we're sort of entering the memory safety era, right? Where we want more and more of our firmware to be written in memory safe programming languages like Rust, because that's how you prevent a vast number of vulnerabilities in the wild. So what is Patina? Patina is, or the Patina Dixie core. Dixie stands for Driver Execution Environment. That's a word that David used earlier as well. And just to help you understand what Dixie means, if you think of UFI as an operating system, it isn't, but if you think of it as an operating system, the Dixie phase is sort of the kernel of the operating system. And so with Patina, we are actually open sourcing the first, to our knowledge, the first sort of completely memory safe Dixie implementation. Patina, as I said, is a pure Rust and memory safe Dixie implementation. We believe the first of its kind. And it supports ARM and x86 64 right from the get-go. This is a really exciting and bold step in the right direction for us and the industry. And if you're interested in learning more, you can, of course, go to the ODP website, but you can also look up a talk that one of our colleagues, Michael Kubaki, he delivered at UFI Plugfest last month, and it's called Patina UFI in Rust, and you can find it on YouTube. Back to David for a deep dive into drivers.
Thanks, Karan. We've talked a lot up to now about the investments we're making for a secure foundation. But secure posture is also getting a major boost thanks to a new effort called WDR, Windows Drivers in Rust. Continuing the theme of memory safety, you'll see Surface not only bringing memory safe drivers to market, we're also co-developing the framework so that anyone can make their drivers more secure and more reliable on Windows. What started as an effort within Surface to explore the feasibility of writing our own drivers in Rust grew into a very active cross-company open source effort called Windows Drivers RS. Driver developers are used to writing drivers in C by linking to libraries included in the Windows Driver Kit, the WDK. And our goal is to ensure that Rust developers can take advantage of the same libraries and headers in the WDK as the C developers can, granting them access to all the DDIs needed to write a Windows driver. This repo contributes the following crates back to the ecosystem. So I'm going to go through them with you guys. It's WDK alloc. This is a custom allocator for kernel pool memory. This is built on Rust primitives. WDK panic. This is a default panic handler, and it enables no STD. So that allows actually driver writers to write very efficiently with only using the core crates. WDK build. It's a library to configure a cargo build script that performs all the downstream linking to the WDK and generates the Rust bindings. WDK sys, this provides the raw FFI, or what we call foreign function interface bindings to APIs that are available in the WDK. This includes both the auto-generated FFI bindings from BindGen as well as any of the manual re-implementations from the macros that BindGen failed to generate. WDK macros is a collection of macros to help you use and interact with WDK sys direct bindings. And lastly, WDK, which provides the safe idiomatic bindings to the APIs available in the WDK. And I'm really excited to share the Cargo WDK. So Cargo tool that we have that actually makes setting up a Rust environment for driver development really, really easy. It just got upstreamed about a week ago to crates.io, and this cargo extension enables developers to create an empty driver project with all necessary linkage, build steps, and dependencies all pre-populated. It's also capable of calling WDK tools like INF Verifier, as you would do when you're building a driver in C in Visual Studio. I'm only going to touch on 3 key things here. So number 1, we support both user mode drivers, UMDF, by spitting out a DLL, and kernel mode drivers, KMDF, via output of a .sys file from CDY-lib today. Number 2, we support FFI bindings for a subset of the WDK today. So think about common APIs from WDF.h, Windows.h for user mode, and NTDDK.h for kernel mode. Number 3, we've made it really easy via declarative configurations of the bindings. So I'm going to talk a little bit more about that. As you can see in this example, by simply declaring the desired driver model and version target in the TOML file, the configs will be generated and emitted, allowing for conditional checks at compile time for both C preprocessor validation and ensuring that the APIs that are being used are actually permissible. We've covered a lot of ground here in a short period of time, but the takeaway I want you to have is that memory-safe drivers are the future, and it will take a village as we embark on this journey. Saying the Windows API surface is broad would be a bit of an understatement, and we definitely want feedback as we continue to prioritize and light up more and more safe abstractions for driver developers to write idiomatic Rust code. I'm now going to pass it back to Karan to talk more about how we're expanding the reach for all of these efforts.
Thank you, David. And this is a word we've been using a little bit already today, open device partnership. And the 3 things that we've talked about today, that's sort of the composition of open device partnership as of today. And ODP is really designed to be an alliance of industry partners. So this is IHVs, silicon vendors, OEMs, to promote secure, reusable, and trusted system software. Now, last month we announced that Surface actually is joining ODP. And that is, the joining part is actually an important point to make here. We are members of this alliance and looking forward to working with other ecosystem partners here. We truly want to collaborate and actually develop this in the open. And what that means is you all are actually encouraged to come along. Go look at the website. It's opendevicepartnership.org. And from there, you can find the repositories that are all public on GitHub, a ton of documentation that we have. And as customers or developers, you're encouraged to come join, contribute ideas on what we should be working on in the future. You can contribute specs, you can contribute source code, or just give us feedback. All right, back to David to sort of close us out here.
Thanks, Karan. Appreciate how you shared how Surface is leading the ecosystem by sharing our joint innovations with Windows through the Open Device Partnership. An important aspect of our strategy and how we lead is through our servicing strategy. Our secure embedded controller firmware, our UEFI, and our Rust drivers will always be kept up to date and secure through Windows Update. This extends to all the software we ship, enabling us to address issues whenever they may arise quickly and giving admins the control they need. Lastly, we spent a lot of time talking about Rust drivers, but it's important for me to mention some of the in-box Windows security features that are also improving the secure posture. They're prominent on Surface devices, or they're enabled by default as recommended. Windows 11, our most secure operating system yet, is helping protect against phishing, malware, ransomware, and other modern threats. And last Ignite, we launched the Windows Resiliency Initiative, which focuses on strengthening the reliability and reducing attack surface. With admin protection, we're enabling more apps and users to run without admin privileges, and implementing stronger controls for apps and drivers through features like Smart App Control. Surface devices support biometrics via Windows Hello with ESS, enabling passkeys as the more secure passwordless sign-in method for websites and apps. I'm really excited about these features, and therefore I'd highly encourage you to attend 2 talks tomorrow for a deep dive. The first is called Inside Windows Security, and it's hosted by Catherine Holdsworth and her amazing team. And the second is Resilient by Design, hosted by Christian Anderker, Vice President for the Windows Resiliency Initiative. Also, you'd be remiss if you don't check out Making AI Easier with Surface Copilot plus PCs and Natural Input. This is hosted by Erica Arnold and Andrea Rubin. Surface devices truly are the best for multimodal input, leveraging touch, pen, precision touchpad, and voice. And so you should definitely check this out. We'd also like to encourage you to read our blogs, but even more importantly, to participate in our developer community. Please engage with us via ODP, the respective GitHub repos for Secure EC, Patina, and WDR. And our last ask is if you are someone in sourcing here, please update your RFPs to make memory safety a requirement. As we come to a close, we both want to convey what drives us personally, and that's being part of the team that builds the most secure PCs on the planet. Really appreciate your time, and hope you guys have a great week here at Ignite. Thank you.